For me as a computing teacher, binary is one of the best things to teach. It's a completely different number system to anything they've come across before, but it also teaches you a huge amount about computers and how they work and where they came from originally, and how the entire concept of computers, of having machines that do all these things for us, how that came about. There isn't a country on earth that doesn't try and lay claim to having invented the computer as we now know it. This that you can see on the screen here is the Manchester Baby, the world's first stored program computer. Imagine even a time where computers couldn't store programs. You turned it on and you had to program everything right from the beginning. The Manchester Baby worked using valves and vacuum tubes, and it wasn't long before we moved on to transistors. Transistors are smaller, they're more efficient, and they're scalable. Over the years, transistors have got smaller and 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 smaller. But from big clunky vacuum tubes right down to really, 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 really small transistors, the same thing has always been true. They're either on or they're off, and everything a computer does comes down to that principle. On or off, yes or no, positive or negative, 1 or 0. And that's binary, folks. So whenever I've taught binary, I've always started with a recap of the number system that we're all familiar with, which is base 10. And the way that I explain it, which I'm sure is the way it's been explained before, but you have ones and you have tens and you have hundreds and you have thousands and so on. And when we count up into these columns. So we count up as far as 9, and when we get to 9 we kind of run out of ones, and then we're into the tens. So then we move from having a 9 to a 10, and then when we continue counting up, we have 11, 12, 13 up as far as 19, and then we kind of run out of spaces there. So then we have 2 lots of 10 and no 1s, and then we continue up as far as 29, and then we run out of 1s again. So then we're at 30, and so on and so on and so on. And we get as far as 99, and then we run out of possible 10s and we run out of 1s, so then we move into the hundreds, so then we get rid of both of those, and then we have 1 lot of 100, no lots of 10, no lots of 1, and then when we count upwards we have 101 up as far as 109, and then when we get to 109 we run out of 1s again, so then we have 1 lot of 10 and then no 0, so 110 and so on. It's kind of telling Granny to suck eggs, but it kind of gets the kids into the right frame of mind, I suppose, to take on a new number system. So that's base 10. So basically you start off on 0, you go up as far as 9, and then you run out of available numbers and you have to move into the next column and so on. And to be honest, ultimately binary works on a very, very similar basis. It's just you have a lot fewer numbers to play with. So here's how binary works. So as an introduction to teaching binary, I would normally have a slide at the very beginning of the lesson, and it'd be one of 2 or 3 possible things depending on the group and the sort of what I thought would work best with them. So for example, in this case it's a picture of 101 Dalmatians, and I would sort of start a discussion with them about how there's only actually 5 Dalmatians, and we'd kind of discuss it a little bit, and they'd count there's obviously only 5 on there, but it says 101, and obviously the book and the film and stuff are called 101. And I would sort of get them into thinking that the two are sort of the same, that 101 and 5 kind of are the same a little bit. Another thing I would sometimes do is I'd have something on the board that says there are 10 kinds of people in the world, those that understand binary and those that don't. And I'll explain those now. So for reasons that we'll come to, 101 and 5 are kind of the same, and there only being 10 kinds of people in the world, those that do and those that don't, implying that 10 and 2 are the same, are things that we will kind of come to. But it kind of gets, it's something that I like to plant in their heads so that when we actually start explaining binary and they start seeing these things coming out on the board, all of a sudden they make these connections. Oh, 101 is 5, or oh, 10 is 2. So when you begin trying to explain binary, here's how I have always done it, and I've never had a class not get it. Some of them have taken longer than others, but I've never had a class not get it. So those aren't particularly neat, but you get the general idea. So imagine there are columns for each of these, columns of 1s and 2s and 4s and 8s and 16s and 32s, and you can probably guess what comes after 32s. And the way I start to explain it is I say, basically, we're going to try and think of a number. So say our number is going to be 1. We're going to try and find out what binary for 1 might look like. And we're going to do it by starting on the left and working towards the right, and basically trying to fit each of these numbers into the one we're looking for and break it down that way, which will make sense in a second. So how many 32s are there in 1? Clearly there are none. So you could, if you wanted to go the whole hog, put a 0 and a 0 and a 0 and a 0 and a 0. How many 1s in 1 are there? There's 1. There's nothing left over. There's nowhere else to go with this. So binary for 1 is 1. Now you have a long string of zeros before that 1, and I guess depending on how far across you're going with these 64s, 128s and so on, you'll have more and more noughts. Personally, I think it's sufficient just simply to put that 1 in binary works out to be 1. Then we move on to 2, and we follow the same logic. So how many 32s are there in 2? Clearly none. How many 16s in 2 are there? Clearly none, and so on. How many 2s in 2 are there? There's 1. There is one lot of 2 in the number 2. Now remember, we can only have 1 or 0 in this column because the binary is 0s and 1s, and that's it. So it's either going to be no lots of 2 or 1 lots of 2, and that's it. And there's 1 lot of 2. So 2 take away 2 equals 0, so we've got nothing left over, so we know there's nothing here, so we know that's a 0. Consequently, 2 in binary is 1, 0. Hence, there are 10 kinds of people in the world that understand binary, those that do and those that don't. There we go. Now, it's not really 10, it's 1, 0. Saying that it's 10 is a bit misleading and confusing, so it's 1, 0, not 10. But the principle's the same. So move on to a 3. 32s into 3, none. 16s into 3, none. 8s into 3, none. 4s into 3, none. 2s into 3, it can only be 1 or 0. We know that there is at least 2 in 3, so it's 1. So 3 take away the 2 equals 1. How many 1s in 1? There's 1. So 1 take away 1 equals 0. There's nothing left over. So 3 in binary is 1, 1. There, we want to delete all of this. Okay, 4 in binary. There it is. 32s into 4, no. 16s into 4, no. 8s into 4, no. 4s into 4, can only be 1 or 0. We know that there's 4 in 4, so the answer is 1. 4 take away that 4, leaves us with nothing, so we know that's nothing, and we know that's nothing, so 1, 0, 0 is 4 in binary. We move on to 5. Think about the 101 Dalmatians thing we looked at before. See if that helps you. Ugh. Let's try that again. Apparently, the one big flaw with graphics tablets is if you've got handwriting as atrocious as mine. 5. That's going to take ages to rub out now. 32s into 5, no. 16s into 5, no. 8s into 5, no. 4s into 5, yes. One of them, we can only get 1 or 0, so it must be a 1. 5 take away that 4, leaves us with 1. How many 2s into that 1? None. How many 1s into that 1? There's 1, so it's a 1. which takes so that's that 1 take away 1 equals 0, so we've finished. So 5 in binary is 1, 0, 1, like 101. Oh, sir, that's why you put that 101 Dalmatians thing up. Oh, sir, you're so cool, said none of them. 6. Hopefully you're getting the flow of this now. 32's into 6, no. 16's into 6, no. 8's into 6, no. 4's into 6, 1. 6, take away that 4, leaves us with 2. So 2's into 2 is 1. So 2 take away that 2 equals 0, which leaves us with nothing, which is 1, 1, 0. That is 6 in binary. Still with me? Let's do as far as 8 at least. Get rid of that 6. There we go. Right, so 7. 32's into 7, no. 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 Oh, yes, one of them. 7 take away that 4 leaves us with 3. 2's into 3 is 1. So 3 take away 2 equals 1. That's what we've got left. Oh, there's 1. Okay, great. So 7 is 4, 2, 1. 4 plus 2 plus 1 makes 7. By this point, I would hope that they're either able to kind of extrapolate what the answer is going to be using these column headings, or they can just kind of figure it out some other way. 1 is clearly 1, 2 is 1. Once they've grasped once they've used up the 2 that they're looking for, the other thing is 0. 2 should be fairly straightforward for them. 2 plus 1 makes the 3, so 3, there'll be one of those and one of those. 4, we'll have one of those and then nothing left, so those two are both 0, so that's 4, 5. 4 plus 5, so that must be a 0. 6, 4 plus 2 means there's nothing left in there. It looks a bit like a 6, but it's a 0, I promise. 7, there's one lot of 4 plus 2 is 6 plus 1 is 7, so that must be that. 8, oh, there's 8, so that's one of those, so that's all zeros. 9, okay, so 8 plus 1 makes 9, so those two must be zeros. 10, right, so 8 plus 2, so those two are both zeros. It does depend a little bit on the room and on the kids. They will probably find their own way into this. Once you've explained the logic of it, they should then begin to kind of grasp it. Another clever thing, and this is something I would do for the ones that are slightly more able, I would suggest as like an extension task. If you're setting some of the kids off on a task where they're just kind of working out numbers up to 30 or something, or whatever it might be, if some of the kids are really getting that really quickly, I would set them a challenge of how to work out as fast as possible, without having to do any kind of workings out and stuff, how to find, say, 15 in binary or 31 in binary, because there is kind of a trick to it, and once they've grasped it, they'll be like, wait, I've figured it out. And some of them may come up with this already. So 15. Now we know, actually let's move these over a little bit. So we're going to try and find 15 in binary and 31 in binary, and maybe let's go for 63 in binary as well, as quickly as we can. So we know that this column is 16s, and we know that 16 is therefore going to be that, and that. 15, therefore, is going to be 1s for all of these columns except 16, because the next available slot then is the 16s. So we know if that column is 16, 15 is going to be all of these other columns. We know if that column's 32, 31 is going to be all of these columns. And we know that 64 is going to be this next column over here. So we know that 63 must be all of these other columns we have available to us. If you can get the kids to grasp that and to be able to kind of predict what the next column is going to be, and therefore what the number before that will be, that's kind of good stuff. And it's a good extension task. It gets them thinking. It gets them taking what they've already learned about binary, what they already understand, and then try and develop that and think around it and problem solve. And obviously that's all good stuff. So 15 in binary, 15 into 8 goes once. 15 take away 8 leaves 7. I have to think for a second there. 4's into 7 goes once, so then 7 take away 4 equals 3. 2's into 3 goes once, so 3 take away 2 equals 1, and then 1 into 1 goes 1. So as well as getting them to kind of predict it, they would also need to be able to prove that their answer is correct. They can't just go, oh, you do this. Is that, yeah, cool, can I go out early? Make them show their workings. It's good practice for every other exam they'll ever have to do in their lives. And that kind of basically is binary. Basically, it's base 2. And once they understand that this can only be 1 or a 0, and that can only be 1 or a 0, and that can only be 1 or a 0, once they kind of understand the logic of that, it helps them then to work out that, it's not that complicated. And also, if you're going to give them things like this to try and work out, whatever it might be. I mean, obviously there's lots and lots of... That's the same one. There we go. There's obviously lots and lots of different ones of these, and I guess depending on how many of... Oh, the 2 disappeared. How many of these columns you begin to use, how far into binary you go, how high the numbers get. Do let them just write down these numbers so they can kind of have something to work with. It's kind of mean not doing so. I've had kids who have sat there looking at this, just trying to work out, what that's 0. Is that ones? So then they're, let them write down the 1, 2, 4, 8, 16 and stuff and work it out that way. Why not? I did. I mean, the more you do it, the more you can at a glance work out what a number in binary is. I remember when I had my very first teacher training interview, one of the things they asked me to interview was to convert some binary into base 10, and they just gave me like something like that. And I said to them, am I allowed to write down these numbers? And they said, yeah, it's fine, it's totally fine. So I did. Because, why wouldn't you make it easier for yourself? And so that, in a nutshell, is binary. That's how I've always taught it. I've taught it on whiteboards. I've taught it on little mini whiteboards in front of them. I've done it on their screens, and so they're all seeing the same thing on their own screens. Whichever way you find of doing it, that's the one that I've used, and I've never had a problem with it. One final thing. A kind of fun thing to do is to leave that on the board or something along those lines. Try and make it look a little bit less, but like a bus in actual fact. I tend to use this as a sort of closing shot, because I'll sort of say to them, if you go home and you look at the remote controls or the power buttons for any of your devices, not phones and stuff so much, but remote controls for TVs and stereos and stuff, presuming they still have these antiquated pieces of technology in their houses. On the power buttons, you'll often find a logo similar to this. It's 1 and 0 in binary, on or off. It's the power button, you see. I had to look quickly to make sure that I actually do have a remote control in the house that has this on it, and they do still seem to, so I feel slightly vindicated. But that's quite a fun little thing for them to take away with them, because then they can go home and go, oh, Dad, look, or Mum, look, oh, the remote control, this, do you know what this is? Do you know what this weird shape is? It's a 1 and a 0 in binary, means on or off. And also, that's the other thing, I guess, is to make sure that when you're teaching them binary, frame it in terms of the fact that it's how computers understand information, because ultimately, you have... I have Russian dolls for this. I've got a Russian doll that's robots. And I sort of explain that you have these sort of different layers of abstraction from kind of what it is that we're typing in on the computer to what that program does with it, and so on through the RAM and all these other things, until basically you end up at the processor level where everything is just 1s and 0s. And having them understand that those 1s and 0s get kind of turned into things variously, or vice versa, so that we can understand computers and they can understand us, but there's all these layers of abstraction between what it is that we understand and what it is that they understand, and how these two entirely disparate sort of representations of information are nevertheless kind of synchronized in some way. It's amazing to me. And also talk about the history of computers, because talking about valves and vacuum tubes and stuff is kind of cool. I'm really just drawing kind of buckets on the screen now. Anyway, that's binary. Ka-chink.